So, we will start this course as power system analysis, and so power system is a core course, power system analysis, for particularly for various places in India, that is the third year undergraduate electrical engineering course. It's a core course, and we will try to cover some of the important topics for this course. So basically, that your power system actually is the largest man-made largest dynamic system on the earth, right? So basically, your first initially we will discuss about structure of power systems and few other aspects, right? So first thing is that generally there are three sections we consider in power system. One is generation, transmission and distribution system are the main components of an electric power system, right? So generating station and distribution systems are connected through transmission lines, right? Normally transmission lines implies the bulk transfer of power by high voltage lines between main load centers, and distribution system is mainly responsible for the conveyance of this power to the consumers by means of lower voltage networks. So generation, then transmission, and then distribution. These are the three main component of this main part of the power system, right? So next one is that if we look into the schematic diagram of a power system, right? If we look into that schematic diagram of a power system, so first one is a large generating station. Mainly they may be thermal, maybe hydro or nuclear power station, right? Then we have a step up transformer. Generally generator terminal voltage in power system, say it depends of course on the rating of the machine and power generating capacity of the generator, but generally it will be 10.8 kV or 11 kV or little bit more, also 11.2 kV. It depends on the design of the generator of this power, in the thermal power plant, hydro power plant or nuclear power plant. Then after this step up transformer is there, then voltage will be stepped up. So there is a transmission system is coming. It will be 400 kV or 220 kV, right? So when it is stepped up, after that this tie line to other system means, tie line means it is basically a three-phase transmission line, and showing just by a single line arrow that thing, because transmission system is a balanced power system, balance it is a three-phase, all the three phases carrying that balanced power. So just showing like this by a single line, the tie line to other system, right? Other system means other power system. It may be power, maybe it is connected to other power system, right? Or it is connected to gone to another substation somewhere, right? Then you have a step down transformer. That means voltage will be stepped down to 132 kV or 66 kV. This portion we call sub transmission system, right? So and after that it is showing here that large industrial consumers. There are many industrial consumers, large industrial consumers. They need power supply at the voltage level 132 kV or 66 kV. That's why it is shown like schematically. It is shown like this. After that, and here also small local independent power producers. Maybe private parties are there who are also generating power. Their power. This is their generating unit. This side same thing, right? And here also you have a this transformer is a step up transformer from generator side to this side, right? And voltage will be either stepped up to 66 or 132 kV, and they are also injecting power to the sub transmission system. These are the local independent power producers. We will assume the private parties, say, right? Then from 132 or 66 kV, it will be further stepped down, right? And then primary distribution system it will come. So primary distribution means it will be 33 kV or 11 kV, right? Here also medium large consumers. There may be some small industries or medium large consumers who need power at the voltage level of 33 or 11 kV. So that thing also connected. So shown like this, and here also at this voltage level 11 kV or 33 kV, you have small embedded generators. For example, wind generators, right? Suppose this wind power, it may be utilities or it may be private parties also, right, and this owned by this generator, right, that wind generator say, right. If you have a solar also other distributed generating units also, no problem. In the case of solar, you have to convert your what you call from DC to AC, right. But anyway, it is shown as the AC power will be injected. So just for the timing, you assume that this is wind generators only, right. And here also this is a step up transformer and power being injected. This same meaning, this side also small embedded generators, both sides shown, right. And then this is a secondary distribution system. The voltage, that is a 400 volt. You might have seen that pole mounted distribution transformer, maybe near your college, near your home, right. So those transformers generally 11 kV by 400 volt or maybe 433 volt, right. So these are small consumers, that 400 volt 3 phase or 230 volt or per phase, right. So in this case, if it is a line to line voltage, then it will be 400 or 430, and if it is your single phase, then line to neutral, then it will be 400. If it is a 400, then 400 by root 3, or if it is a 430, then 430 by root 3, right. So whatever it comes, so I have just written 230 volt per phase, right. So this is a schematic diagram of a as a whole, as a power system, right. So I mean this is just for just how the power system is, I mean from generating station to the distribution system. In between, transmission and sub transmission systems are there, particularly 132 or 66 kV transmission line, we are calling it as a sub transmission system, right. Then take this part of a power system. So if we take, like, these are all small rectangular boxes are shown, these are basically circuit breakers, right. And suppose you have a generating station, this is generating stations. So everywhere you have these all transformers are step up transformer, generator transformers, right. This is, I have drawn just to show that there is a part of a power system. Then it is all are coming to substations, right. These lines are coming from here and there to substations, and again here all these feeders, it is going to the loads. This is step down transformer again. This is also same thing to the loads, and these are all loads. These are all showing load, and here also it may be going to the other part of the system, so to rest of the system, and these are embedded generators, right. For example, wind power generator. So this is a simple structure of the part of the power system, right. And it may be basically this is the simplest way, but in a power network you have so many generators and so many transmission lines, right. And those we will see how to how to solve all these things when we will come to the what you call that power flow or load flow studies, right. So these are the schematic diagram of this thing, part of a power system. Next one is that from sub transmission system, this is a typical distribution systems, right. Before saying anything, when these lines I have made, means a 3-phase line, and when two such things are there, that is single phase, right. Because sometimes we need 3-phase, particularly for the commercial places, we need 3-phase power supply, but a residential area, say at home, we need single phase power supply. These are fuses, right. And for example, this is 66 by 11 kV, this thing, these are all boxes shown in circuit breakers. These are reclosers, it is going to additional feeders, right. And this all transformer, these are pole mounted distribution transformer, they are 11, I have written 11 kV by 400 volt, it may be 11 kV by 430 or 440 volt also, right. These are all pole mounted distribution transformers, and these are section point, it may be closed, maybe this thing may be open, right. And another thing is that this is your normally open tie switch, right. So this is a tie switch, means this is a your three phase, basically a 3-phase line, but one sectionalizer will be there, right. If you, I mean, if you want to operate manually, right, nowadays with sophisticated your control technique, it can be automatically switched on or off. But why this is normally open, as far as when power is being supplied by both sides and there is no fault or no outage of the line, then things are okay. But suppose something has happened, some fault has occurred here, for example, say, right, or some fault has occurred here, then what we can do is that this line can be isolated, this can be isolated, and this should be closed such that power can come through this and it can supply the affected your affected zone. But as soon as you open this portion unaffected, because power will come from this, but when something has happened here, this portion will not get power. So suppose this is open and you close this one, so power will come from this side, right. So that's why it is called normally open tie switches, and this is something is written to secondary distribution system, right. So these are all pole mounted your transformer, and here it is showing 66 by 11 kV, but many parts or hilly area it may not be 11 kV, some cases it has low voltage level, maybe 6.6 kV, some cases even 3.3 kV, right. But standard in this thing is 11 kV most of the places you can see, right. And these are the schematic diagram of typical distribution system, right. So what we have discussed now little bit about your power system, generating side, then transmission, and then distribution side, right. Next is the reasons for interconnection, right, because many power systems they are interconnected together. So generating station and distribution system are connected through transmission lines. It has to be, because bulk power will transfer through transmission line only. The transmission system of a particular area, say state, is known as a grid, right. And this way you can define when one can define in other way also, but generally the transmission of a particular area, say a region, is suppose for example state is known as a grid. Now different grids are interconnected through tie lines. Tie line means it's a three-phase transmission line, right, to form a regional grid, so also called power pools, right. This is actually power pools, right. So the different grids, when they will be interconnected through tie lines, that means three-phase line, that it will form a regional grid also, and this is also called power pools, right. And different regional grids are further connected to form a national grid. So transmission system of a particular area is known as a grid, and different grids are interconnected to three-phase lines, that is tie lines, that means they are tied together. Suppose two grids are interconnected by so through tie lines, right, to form a regional grid, and different regional grids are further connected to form a national grid, right. So these are the meaning of this your what you call that grid, regional grid and national grid. So next is that reason for interconnection. Now cooperative assistance is one of the planned benefits of interconnected operation, because when 3-4 power systems are interconnected together, so basically this is for cooperative assistance, right. Interconnected operation is always economical and reliable, right. More we will see later, right, when we will come to the different topic. So it is always economical and very much your reliable, right, for this thing. Economic advantage of interconnection is to reduce the reserve generation capacity in each area. Details, though at this present it is just I am giving you that your basic thing. When we will come to the different topic, more thing can be discussed, right, later, right. But economic advantage of inter is to reduce the reserve generation capacity in each area. I mean each area means it is a power system, right. So when so many power systems are interconnected, so in that case reserve generation capacity in each area it can be reduced. Later I will try to explain, right. If there is sudden increase of load or loss of generation in one area, it is possible to borrow power from adjoining interconnected areas, right. It is something like this. For example, suppose you have this is one power system, say area 1. Suppose it is connected to another one, area 2. Suppose it is connected to another one, area 3, right. Suppose another one is there, right, say area 4, it is also connected, say this one also connected, right. So suppose 4 areas are there, 4 different things, but they are all connected, they are all interconnected. So if suppose everywhere it is power system, this is here it is one area 1, area 2, area 3, area 4, each one is a power system, everyone is having a power demand, every generating unit is generating power to supply its load, right. Here also, suppose sometimes it may happen that your this area it needs power from the other areas, because here load demand is more but its generation capacity is less. So at that time this particular area can borrow or purchase power from these 3 areas if it is interconnected, right. That means although here load is more, generation is less, that means its reserve capacity is less, but it can, assuming that this power system they have the sufficient reserve capacity, then it can borrow power from other interconnected power system. So this is that is your that is the advantage. That means economic advantage of interconnection is to reduce the reserve generation capacity in each area. Now if there is a sudden increase in load or loss of generation in one area, it is possible to borrow power from adjoining interconnected area. That means suppose load has increased, I told you that it can borrow power from this power system, from these 3 power systems. Or suppose you have, for example, here you have 5 generating units, say 5 generating units, right. Suppose one of the generating units, right, your what you call suddenly stopped, I mean loss of generation. So 4 units are there. So load generation will be much less, load will be more, right. So in that case, from these adjoining areas, interconnected area power systems, that this additional load can be supplied from these power systems, if they assuming they have the sufficient generating capacity, right, such that they can supply that this additional load. So that's why that if there is sudden increase of load or loss of generation in one area, it is possible to borrow power from adjoining interconnected areas. So these are the major advantage of interconnected operation, right. Now to meet sudden increase of load, a certain amount of generating capacity in each area known as the spinning reserve is required, right. I mean load suddenly increases and initially you want to and immediately you want to supply this additional load, right, and that means a certain amount of generating capacity in each area known as the spinning reserve is required. This consists of generators running at normal speed and ready to supply power instantaneously. That means, I mean they should I mean as soon as the load has increased, right, that this generators, I mean spinning reserve means this consists of generators running at normal speed and ready to supply power up instantaneously. For example, it is always better to keep gas turbine and hydro generators spinning reserve. The reason is gas turbines can be started and loaded in just 3 minutes or less, because it is very it can generate power very quickly, gas turbine, or hydro units can be even quicker, right. So this gas turbines and hydro units, these two generating your what you call power generating units, they will be very useful as a spinning reserve. Suppose if load has suddenly increased, but you don't have sufficient this thing your what you call sufficient capacity to this thing that you have to immediately supply that load. So in that case your gas turbine or hydro units will be very effective, because they can generate power very quickly, right. Thermal power plant, I mean, if it is a thermal unit, it has some limitation. Later if possible I will tell you. Thermal hydro generates power very quickly, doesn't have any, I mean that constant is not stringent type, whereas hydro case for thermal case that constant is very stringent type, sorry, but hydro case it can generate power very quickly, right. So that's why gas turbines or hydro turbines, hydro generating units, they should be they should be kept as a spinning reserve. Next is, so these are general ideas that are some advantages of interconnected power system, right. Next is that load characteristics. So general nature of load is characterized by load factor, then demand factor, then diversity factor, power factor and utilization factor. There are some more factors, later we will see. In general, the types of load can be divided into following categories. There are 4 categories. domestic, commercial, industrial and agriculture, right. So, domestic loads, this you will be knowing what is domestic load. Domestic load mainly consists of lights, fans, refrigerators, air conditioners, mixer grinders, heaters, ovens, small pumping motors, etc. These are domestic loads, right. Similarly, commercial loads basically lighting for shops, then offices, then advertisements, etc., fans, heating, then air conditioning again, and many other electrical appliances used in marketplaces, restaurant, etc. So, domestic load, then commercial loads, right. So, generally, so loads of and different load, domestic, commercial, industrial, agriculture, they have different type of characteristic. So, next is this thing, that industrial loads. So, industrial loads, at the time of talking about this power system thing, I told you that industrial basically it takes power at very high voltage level, particularly large industries. So, industrial loads consist of small scale industries, medium scale industries, large scale industries, heavy industries and cottage industries. These are falling under industrial loads, right. Their load curve will be different, your commercial will be different, right. Then domestic will be different. Next, agricultural load basically is a mainly motor pump sets, right, for this integration purposes. So, agricultural loads. So, there are 4 different type of loads. Now, after this, that power factor of various equipments, right. For example, induction motors generally 0.6 to 0.85, then fractional horsepower motors 0.5 to 0.8, then fluorescent lamps 0.55 to 0.90, then fans 0.55 to 0.85, and these are some data. Induction furnaces 0.7 to 0.85, and then arc welders 0.35 to 0.5. These are the range of power factors for various your equipments, electrical equipments. Some ideas regarding the power factor of the some your equipments, right. Next is basic definition of commonly used terms, right. So, first is we talk about the connected load. This is a common sense you can apply, that what will be the connected load. So, each electrical device has its rated capacity. Every device, electrical equipment or component, it has its own rated capacity. The sum of the continuous ratings of all the electrical devices connected to the supply system is known as connected load. For example, you take the example of your home, right. Light, fans, AC and other thing, geyser and other things, right. So, if you add their total rated capacity, then that will be the connected load of your home, right. So, these are called, is known as a connected load, right. Then demand, the demand of an installation or system, right, is the load at the receiving terminals, right, averaged over a specified interval of time. I mean, demand of an installation or system is the load at the receiving terminals averaged over a specified interval of time. That means you have some time definition and take the load at every hour or every half an hour whatsoever. After that, you make the average of it over a given interval of time, right. Here the load may be given in kilowatt, maybe kilovolt kVA or kilo ampere or amperes, the way you define, but generally in power system mostly we will define kilowatt or kVA, right. Then demand interval, it is the time period over which the average load is computed. Suppose for a day you have a 24 hours, so every hour load then if you try to compute the average load for 24 hours, right. So, that is the 24 hours is the demand interval, that is the time period over which the average load is computed. We will take many example, at that time you will see, right. So, connected load, demand interval. Next is maximum demand. This maximum demand of an installation or is the greatest of all demands which have occurred during the specified period of time. Some specified time is period is specified, and then maximum demand of an installation is the greatest of the demands which have occurred during that specified period of time. Suppose you have a say you take from your today this thing from midnight to next midnight, so 24 hours. During 24 hours you see that for a particular installation of system, demand is increasing and decreasing. So this 24 hours you take note down what is the maximum demand. So that's why during the specified period of time, that will be the maximum demand, right. Then another thing is, another terminology they use, that coincident demand or diversified demand, right. It is the demand of the composite group as a whole, right, of somewhat unrelated loads over a specified period of time, right. So you have a different composite group, not only on the single load, there may be many, right, and some industrial, commercial, agriculture, domestic, say different groups you have, right, over a specified period. So it is the demand of composite group as a whole of somewhat unrelated loads over a specified period of time. It is the maximum sum of the contributions of the individual demands to the diversified demand over a specific time interval. So everywhere we have time interval is specified, right. So it is the maximum sum of the contribution of the individual demands, right, to the diversified demand over a specified time. That every hour, suppose you have a 4 groups of load, every hour you are adding those load, and we are trying to find out what is the maximum sum, right, of the individual demand to the diversified demand over a specific time interval, right. So this is called coincident demand. Then non-coincident demand, it is the sum of the demands of a group of loads with no restriction on the interval to which each demand is applicable. So in that case, your what you call that your interval is not no restriction of the interval. So it is just the sum of the demands of a group of loads with no restriction on the interval to which each demand is applicable, right. This is called sometimes non-coincident demand, right. Next is another one is demand factor. It is the ratio of the maximum demand of a system to the total connected load of the system. Thus the demand factor we define DF is given as. So it is the ratio of the maximum demand of the system to the total connected load. So demand factor can be given as maximum demand divided by total connected load. So this is say equation 1, right. The demand factor is usually less than 1, because generally if maximum demand is equal to total connected load, then it will be your what you call only 1. Otherwise generally maximum demand is, because at a home you have all light, fan, switches, everything, light, fan, TV, refrigerator, geyser, everything is there, all you are not switching on at one time. So naturally maximum demand will be less than the total connected load, so usually less than 1, right. So demand factor gives an indication of the simultaneous operation of the total connected load, right. Next is utilization factor. So it is the ratio of the maximum demand of a system to the rated capacity of the system, right. So later this is we define, that is the ratio of the maximum demand of a system to the rated capacity of the system. So utilization factor you define UF is can be given as maximum demand of the system divided by rated system capacity, right. So this is equation 2. And next one is plant factor. Sometimes this plant factor also known as capacity factor or use factor. It is the ratio of the total actual energy produced over a specified period of time to the energy that would have been produced if the plant or generating units had operated continuously at maximum rating, right. So this is known as plant factor, capacity factor or use factor. This is particularly for the generating station, this terminology is true, right. So it is the ratio of the total actual energy produced over a specified period of time, say annual, to the say annually how much energy that was produced to the energy that would have been produced if the plant generating units had operated continuously at maximum rating. So this is called plant utilization, plant factor or capacity factor or use factor.